All right, so we're into chapter 6 here. So this is 6.1. Now, all of chapter 6 is about rational functions, and I like to call rational functions by a different name. I call these fancy fractions, because all they are is fractions with polynomials in them. So for this first section, we're just focusing on multiplying and dividing. So this is a 3-objective section. The first is to find the domain of a rational. And that is function. Now I'm going to say rational instead of rational function a lot. So just know in this chapter and moving forward, whenever you hear me say rational, I mean rational function. I'm just a little lazy and I dropped the function. All right, the second objective is to simplify rational functions. And our final objective is to multiply and divide. Rational functions. So, can't start without defining rational function. A rational function is a ratio of two polynomials, p of x over q of x, and as I said before, you can think of these as just fancy fractions because they just have polynomials. So here's two examples here. Both of these are rationals. They have different polynomials in their numerator and denominator. Technically, 1 over 2 is also a rational function. It's a constant rational function because 1 and 2 are polynomials that are just constant polynomials. Boring ones, but they do still count. And so this is why I just think of these as fractions. So if you don't like fractions that much, or fractions scare you, now is a good time to go back and review your basic fraction rules, because everything translates to rational functions perfectly. The one thing that rational functions have unique to is, since they're functions, we talk about domains. So the domain of a rational function is entirely determined by its denominator. Because numerators can be whatever we want, but the denominator, the divisor, you are only not allowed to divide by one number in existence, and that is wherever the denominator is equal to 0. Can't divide by 0. We say the function is undefined. And so our domains for rationals are always exclusively written in terms of what they can't be instead of what they can be. So you'll see what I mean by that in these 3 examples. So find the domain of the following functions. So to find the domain of a rational, we just look at its denominator and we set it equal to 0. In this case, we get 1. And this is where this function is undefined, so our domain is actually just x cannot equal 1. And we typically just write it like that because it can be any other number in existence, but we can't have x equal 1. So moving on to number 2 here, again, we just focus on the denominator, setting it equal to 0. This is going to factor nicely to x minus 5 times x plus 3. This gives us x equals 5 and negative 3, and we know our domain then is simply that we cannot let x equal 5 or negative 3, because it will make our function undefined. Okay, moving on here to number 3 here, x squared plus 7, setting it equal to 0. So this is then x squared equals negative 7, and so now you should stop. Red flag should be raised in your head. If you square a number, it's always positive, no matter what. So this will never work, which means our denominator never equals 0. And so our domain is negative infinity to infinity. Or the symbol for this is all real numbers. It's this funny looking R with an extra leg. So you've got a couple practice problems here to try out on your own, identifying domains. It's basically what we were doing in chapter 5, where we were solving polynomial equations. Set your denominator, which is a polynomial, equal to 0, factor and solve. So flipping the page here, we're going to do some simplifying before we do the definition. So when it says simplify the rational function, the first thing we want to do is factor everything as much as we can. So this one on top has already been factored nicely for us to x plus 2 quantity squared. X squared minus 4 is one of our special products, and we know this to be x minus 2 times x plus 2. And now we are allowed to cancel one of the x plus 2's from the numerator with this x plus 2 in the denominator, and this gives us x plus 2 over x minus 2 is the simplified version. And number, this shouldn't be 5, it should be 1, 2, 3 again. The numbering continued from the last one. I think yours is fixed already. So in the next one, 2x squared, 10x cubed minus 2x squared on the bottom. So we can't factor the numerator, but the denominator has a 2x squared that can be pulled out. So this is 5x minus 1 left over. Cancel everything. Now when everything gets canceled, there's actually a 1 since it's division. It's a fraction bar, it's a division bar. So this becomes 1 over 5x minus 1 is our simplified version. And then over here, this is 9x squared plus 12x plus 4. So we need to factor this numerator, factors nicely to 3x plus 2 quantity squared. And the denominator, 8x squared plus x minus 7, factors nicely to 8x minus 7 times x plus 1. Now when we have factored it fully, and you notice there's no cancellations we can make now from any of these, it means that the rational is already fully factored. Now, the fundamental principle of simplifying rational expressions is what we were using there. And so for any rational expression p over q and any polynomial r where r is not 0, so where you can't plug in a number and equal it to 0, PR over QR just equals P over Q. So this is what we were using here. We found the R that was hidden and canceled it. Now this is an extremely important note here. Simplifying a rational function does not change its domain. So even though on this one we've eliminated x plus 2, at x plus 2, the domain is still x cannot equal 2 or negative 2. Now what this tells us is a canceled, I think canceled has 2 L's, maybe not. A canceled root is called a removable discontinuity. Or a whole. So that when we get to graphing rationals at the end of this chapter, we're going to see a lot of different types of discontinuities, which is where the domain is undefined, those values. And when you can cancel one of them, it looks like a whole. So this isn't too important for this section, but it will be useful in a later section in this chapter. So that's how you simplify. You just factor and cancel, and then just make sure you understand if you have to find domain, do that first before you reduce. So when we multiply rational functions, the rule for multiplying rational functions is the same rule for multiplying fractions. So if we have p over q times r over s, this is just pr over qs. You just multiply straight across. And this also means that we get cross cancellations just like we do with fractions, so you typically will factor everything first and then cancel as much as you can. So let's illustrate that in these 3 examples here. So the first thing we're going to do is factor everything. 3n plus 1 can't be factored. 2n can't be factored. I can factor a GCF of 2 out of here to 2 times n minus 2. And 3n squared minus 2n minus 1 factors nicely to 3n plus 1 times n minus 1. And so since we have cross-canceling, we can cancel this, becomes a 1 with this. We can cancel this 2 with this 2, and you can do a cleanup step, or you can skip this. I like to do the cleanup step. 1 over n times n minus 2 over n minus 1 gives us n minus 2 over n times n minus 1. Now I can't remember off the top of my head if the homework asks you to distribute a value like this. If you ever get marked wrong on a quiz or a test because you didn't distribute, just let me know. It's one of the reasons you do the scratch work, so I can give you those points back, because this is good enough for me. This tells me you know exactly what you're doing. Okay, moving on to number 2 here. X cubed minus 1. Now this is a special factorization that I talked about in the optional review module, where I went into a little more detail on some other things. So this actually factors to x squared plus x plus 1 times x minus 1 over, factoring the bottom, negative 3 out, x minus 1 times 15x squared, and x squared plus x plus 1 is not going to factor at all. So this allows me to cancel this term, this term, this term, this term, this negative 3 with this 15 to make it negative 5. And I'm going to skip the cleanup step. So this is a 1, a 1, a 1, a 1 now, and this is a 1. And so what's left is negative 5x squared. Now this factorization is called a difference of cubes. Now I put it in here just because this is an example from a different class, a different algebra class. If you're curious about this factorization technique, it's in the optional review module in Canvas. And if you want to just Google it and see what it is, it'll show you that as well. There's also a sum of cubes, which looks very similar. So moving on to number 3 then. This one doesn't have a lot of factoring, but I'm going to do some rewriting here. So I'm going to make this x squared plus 3 over negative x minus 3, factoring out a negative, x plus 3 here, and this is a difference of squares, x squared minus 3 times x squared plus 3. So I can cancel the x squared plus 3's. Nothing else can be canceled. So what I have left is x plus 3 over x minus 3 with a negative times x squared minus 3. So sometimes our factorizations, our cancellations, when we multiply, don't necessarily make it super nice like this, or even like this. Sometimes it still looks a little gross. But you just cancel everything that you can, and you don't cancel more than that. So, turn the page. Talking about dividing here. So again, the rule for dividing rational functions is the same rule for dividing fractions. So if you have p over q divided by r over s, that's a 3, not an s, there we go. Then this is equal to p over q multiplied by the reciprocal s over r. So we'll look at 2 examples, and then there's some practice problems for you to finish up on your own. So this becomes 8m squared. I'm going to factor the 3 out and make this m minus 4. Times, flipping this and factoring a negative out of the bottom, this is m minus 2 all over 40. So I can cancel an 8 out of this 40 and make this a 6. And it doesn't look like I have any more cancellations I can make. So this just becomes negative m squared times m minus 2 over 18 times m minus 4. Nothing else we can do there. And number 2, all of these things need to be factored. So 18y squared plus 9y minus 2 will factor to 6y minus 1 times 3y plus 2. 24y squared minus 10y plus 1 will factor to 6y minus 1 times 4y minus 1. I'm going to flip, so factoring 8y squared plus 18y minus 5 gets us 4y minus 1 times 2y plus 5. And then factoring 3y squared plus 17y plus 10 gives us 3y plus 2 times y plus 5. So looking at my cancellations, this 6y minus 1 and this 6y minus 1 will cancel. The 4y minus 1s will cancel. The 3y minus 2 or plus 2s will cancel. And this is now 1 over 1 times 2y plus 5 over y plus 5. And please remember, these are come together, so you cannot cancel a plus 5. It's attached to this piece with that addition symbol. You can't cancel the 5s, even though they're both 5s. It's two different binomials, and if you have trouble remembering that, keep your parentheses on there and it'll make it a little bit easier. Alright, so that's the end of 6.1. In the next section, we'll be adding and subtracting rationals.